Okay. Hello, everyone. I'm William Parkinson. My role at Urthecast is as a research manager. What this typically looks like is I sit in a dark room and I read an endless stream of journal articles and pretend to be smart. And there's a number of very smart people in this room, so what I'm hoping to get out of this is that you tear everything I say apart and tell me all the things I'm doing wrong so that I can fix that, because this is more of a kind of a strategy session more than it is kind of what we've done. So this is all a presentation talking about Earth Daily, so I'm going to dive into that problem as I see it and as it fits in the context of analysis-ready data. I'm going to start very high level. This is not news for anyone. You know, why do we do ARD? We're all about monitoring and assessing landscape change, reducing the data processing for application scientists, obviously. And at the end of the day, it's really about understanding and producing some sort of time series product that is ready for analysis. And there's lots of great examples of why we do this over long time periods. There's lots of success stories. So for example, here we have a nice 10-year monitoring using 2 different sensors to try and monitor the growth and regrowth and burn rate of different areas of the landscape. And this is actually proving quite successful, and we're able to draw these kind of nice trend lines and model fits through them. But as we zoom into very small time scales, such as a single growing season, the uncertainty associated with different measurements gets higher and higher because it's really hard to draw these trend lines. So this is a bit of an exaggeration and a little fuzzy, but as our uncertainty grows higher and we're looking at a very small time scale, it's really hard to detect subtle change. And so in order to understand small changes in the landscape, such as stress and pests and things like this, we drastically need to reduce these uncertainties. So analysis-ready data. This is my interpretation. Of course, everyone's going to have a slightly different. That's a nice little visual from the Australian Data Cube and kind of the pre-processing they do. And I broadly categorize these into 2 big categories, as I articulate it. Just information generation, so that's a lot of the normalization processes, geolocation, calibration, and then an access problem, so STAC, effectively. In my world, I consider access not my domain, so I'm just going to say that's a solved problem. I'm particularly interested in geolocation, calibration, and atmospheric correction. And so Earth Daily is a satellite constellation. The goal here is for these satellites to be as identical as possible. The goal really being for us to be able to image the Earth and not necessarily care what sensor that image comes from. And so our sensors effectively need to be as identical as possible. And for those who build satellites, even if you try and build all these satellites to the exact same specifications, that's not really going to happen. So there's a lot of stuff that has to happen in order to make these as identical as possible. The nice part is, if we keep this in mind in terms of the purpose, measuring these measurements through time, is that our mission problems that we have to solve already, geometry, radiometry, are very similar to our ARD problems. And in my world, because I work on both of these sides, we're actually able to kind of solve these together in a holistic strategy. So for this talk, I'm mostly just going to be focusing on the radiometry problem, how we can make our sensors as similar to each other as possible. That's not to be confused with the absolute radiometry problem, aka how correct is it to a true measurement. I just want our sensors to be as similar as possible, even if that measurement isn't 100% correct. So, as a data provider, there's a lot of things we have to consider on the geometry radiometry side. A variety of them we can understand reasonably well depending on how we design our orbit, how we design our sensors. Some of them are a little bit more difficult, such as BRDF, and same on the geometry side. But as we kind of start to bring multiple data sets together in a time series sense, we have a big difficulty in understanding that through time because there's more and more variables that all affect each other. So what we see here is we have some that we understand reasonably well, but we see that they all have a big impact from things such as atmosphere, BRDF, and land cover. And so traditionally, as a producer of data, we focus on things that we can control. The RSR, the PSF, the look angle, the sensor resolution, the bit depth, and the sun angle. And then we kind of externalize some of the bigger, more difficult sciencey problems to the users. And so the users go out and they build their data cubes and they try and push all this together. The problem is this is still a problem in calibrating a heterogeneous satellite constellation, or even if they're similar. So what I want to talk about is how these impact our capacity to make our constellation as similar as possible. So if we're trying to calibrate our sensors to each other, all of these play a huge role in the correctness of our ability to calibrate those sensors. And the problem is, of course, they're all very interrelated. How the landscape reflects light is dependent on land cover and look angle and sun angle. how the atmosphere is changing affects how we can calibrate between those sensors. And of course, because this is all happening in a large system, we can't easily know what's going on. So what we typically do is we try to go and calibrate over well-monitored, well-understood sites, pick sites, etc. And we spend a lot of time and money trying to understand those very specific sites and making really strong measurements. We also do things like choose large, reasonably homogeneous land cover areas and try and get the nice reflectance understanding, limit our clouds. And one thing that we've seen a few times as well is limiting that time window for calibration as much. So when we're trying to calibrate two different sensors, say Landsat and Sentinel-2, is we try and find these time windows where they actually image a similar area within a very small time period. And this allows us to do a few assumptions. But how much time is enough time? Well, standing on the shoulder of giants is a good way to start. So there are cases in the past where we have had calibration opportunities that were designed into the missions themselves. So Landsat 5.7, Landsat 4.5, at the beginnings of those missions, they started their orbit in these small time windows, with the core goal being to calibrate those sensors. And what this told us, and what they assumed, was if we had time periods of less than 30 minutes on an acquisition, the atmospheric changes would be small enough under a variety of conditions that we actually don't have to consider the changes in atmosphere in order to calibrate. And this is a big deal, because now we can image the Earth and not worry about the changes between our images in terms of atmosphere in order to calibrate properly. So going back to this mission here, in the Landsat 5.7 example, they actually had a tandem-like orbit, so they were very close together in terms of imaging the Earth. This isn't quite like that, but we are hitting that time window. But we're not done yet, because that tandem or similar time window is not enough. We've only really minimized the atmospheric effects between sensors. There's still lots of impacts on calibration, as we know, a number of them associated with spectral band difference effects, both involved with land cover and atmosphere. And so I want to dive a little bit into those, because those do play a role, and even though our sensors are designed the same, they won't necessarily be all the same once they're on orbit, because of just the nature of this world. And so we just want to understand how much of a role they can play and impact, and how similar our satellites need to be in order to actually properly calibrate them. So for those, many of you know, some of you don't, so simply put, spectral band difference effects are just responses and differences due to different sensitivities and wavelength. And so a nice simple example here is we have two different band 4s that have slightly different RSR curves, and so we'll get slightly different signal responses. Now, if we want to calibrate those two bands, we have to account for differences that are associated with the differences between the bands as well as the differences between surfaces. But the interesting part about this is if our bands are similar enough to each other, say 3% or less, other uncertainties become more important, which means all we really need to verify is that our bands are similar enough to calibrate. And if they're similar enough, things such as land cover differences become way less important. And this is also the case in the atmosphere. So a number of experiments were done on varying the atmosphere and seeing how that affects calibration. And so these are kind of a worst case scenario examples where if we have no clue what the ozone layer is and we kind of guess the extremes that it could be, how does that impact our calibration in the context of our RSR curves? And what we see is that worst case scenario, if we know nothing about ozone, it could affect that 1.3%, but that also assumes our bands are very different. AOD is actually quite negligible in the context of calibration, even though of course it's super important in terms of absolute measurements. And water vapor worst case scenario gets to about 6%. But if we actually look at sensors that are quite similar to each other, all of these actually play a minimum role. So this sounds great. We've basically said, you know what, land cover doesn't matter, atmosphere doesn't matter, we can calibrate and everything's going to be wonderful. And it sounds quite nice. The problem is all of this analysis and all of these assumptions basically assume we're looking at nadir straight down at our targets. And that's not the case we have for Earth Daily. So for Earth Daily, we're imaging the Earth, we have our platforms flying over, they're imaging in these roughly 30 minutes or less windows, and we have these calibration opportunities that are happening on every orbit, ongoing basically through the lifetime. But this poses a whole new set of problems, which is our look angle effect. And this is the big hole in this whole calibration strategy. So traditionally, all the traditional sources of this uncertainty in calibration have been minimized in order to make our sensors as similar as possible. But the problem of non-nadir overlap being used for calibration is not very well addressed in the literature. And so we do have some advantages. We're going to have a situation where we have an ongoing and continuous calibration opportunity on every orbit. We have other sensors on orbit in which we can try and analyze and look at and to understand these problems. And so we believe we're going to be able to statistically address this problem of non-nadir overlap because we're going to have a lot more data coming in on an ongoing basis. And so that's the main way that we're going to try and intercalibrate these sensors. Now the other part of ARD, which is of course temporal differences between those in time, I'm not going to talk into those in any depth other than to say, obviously we want to remove cloud cover. There's lots of ways we can do it. We've seen some of those ways presented. That's a whole separate talk that I'll be talking about at a later time. So for Earth Daily and calibration error in the context of this relative calibration, we've basically narrowed this whole thing down to solving one problem, which is BRDF. And so in the future, you should be able to see a talk on how to handle that problem. Another thing that we're looking at, and it's somewhat related, is of course the absolute calibration, which is a separate problem to solve. Again, the main goal here is to get our measurements to be similar, and of course temporal normalization of Earth Daily. The one thing I want to present at the end, which is a bit orthogonal to this particular talk, is this is actually a slide that I stole from a guy named Mike Wolder at the Pacific Forest Research Center, and I really like it because I think it solves, it's complementary to those other diagrams we keep seeing of this data glut that we keep seeing in remote sensing. Because it's not enough just to handle the amount of data coming in. If our goal here is to increase the number of users and therefore make our data more accessible at less skill, we need to think about what those users are. And I think we're still focusing a lot of our time here on 1 and 2, which is data pre-processing and building these refined products and time series and things like this. But I think what we really want to do as an industry is get to 3 and 4. And I'm not sure what that is. I've nominally put here a term I stole from a colleague of mine, customer-ready data. And who that customer is still a little unknown. But I think if our goal is to make our data more usable, more viable, we need to think about new types of users that want to use our data and what those information products need to look like. And that's it. Thanks.
What is the mean local time you're going to be flying here?
Sorry, can you repeat?
Local time. What's your crossing time?
Yeah, we're aiming at 10:30 local time. Oh, sorry. The local imaging time we're targeting is 10:30 local time, 10:30 a.m.
So that's kind of in between Landsat and Sentinel, so you'll have opportunities for cross-calibration
Yes.
on a pretty regular basis with those stations.
Yes, definitely. That is definitely part of the strategy for that, for sure. Yeah.
I want to commend you for a tight, short talk.
Thank you.
Perfect. I have one question.
Yeah.
So,
I think this is very interesting. It's something we've been discussing with Keith a lot, which is this idea of field of view and what portion of the field of view really is calibratable and usable.
Yeah.
Do you think we should start rethinking what we consider a real revisit rate in a very swath, very wide field of view type of satellite where only the center of the field of view might be calibratable? Can we talk about radiometric revisit times or something like that, or for time series analysis?
I think that we can calibrate wide field of view sensors. I don't think it's a solved problem. But I think it's the type of problem that if we break it down into smaller pieces, we can understand the individual problems as we go into wider field of views. So obviously at Nadir we have a kind of a well understood way in which we can calibrate in a meaningful way. And I think there's a lot of research that starts to understand that as we vary our view just a little bit. And so I think if we break this problem down into smaller chunks, there is a way in which we can do that. But I'm not going to comment too deeply on what that way would be. Yeah.
I can add to that a little bit. The discussion I'm having with Ignacio here is really about radiometric revisit. So BRDF is a big issue.
Yep.
All right. And I'm glad that you are recognizing the issue there. I believe last time I heard it was kind of like on an 8-day revisit. And so the point that BRDF radiometrically consistent, but if you take day 1 versus day 2, the BRDF is different. Unless you know enough about the land cover class, you can't take that BRDF out.
Mhm.
And so now your radiometric revisit from a machine learning consistency and all that kind of stuff really truly is 8 days as opposed to on a daily basis. If you're looking at a field of corn on a daily basis, you're actually getting 8 different BRDF measurements across that field of corn.
Yep.
And now you start to lose that kind of daily cadence of revisit to that field of corn. So you're not really sure, am I seeing a BRDF change or am I seeing something else
Yep.
that's more fundamental about the vegetation or whatever land class you're looking at.
I think you're right. What I would say is I'd go back to this slide and say, if we could truly understand that and have a consistent BRDF, say on the 8-day revisit example, obviously that's not something we can articulate to people who don't understand remote sensing very well, but that doesn't mean we can't bake those assumptions into products we build. Maybe we have those products that say, you should only use these in this type of way because the BRDF is consistent or because the data is consistent. We don't even necessarily have to teach them what BRDF is. But understanding that problem is the first step, and then using that and understanding where it's normalized and then pushing that data out in a meaningful way makes the data more usable.
Okay. Taking Ignacio's question one step further, have you sat down and actually tried to quantify the kind of BRDF variation you have across the swap?
We're in the process of doing that now. Yes.
There's a couple interesting papers I'll share with you later on.
I would love to.
Quantify how much BRDF there is in Sentinel-2, which is a very wide swath. It's not quite as wide a swath, but it's a wide swath, and there is substantial variation across it. So
Yep.
we can discuss afterwards.
I would love to.
I mean,
Oh.
yeah, go ahead.
Like I say, it's a really interesting problem. So a couple of years ago, we had 2,500 Spot 5 images that we had a similar problem. Spot 5 is unemployable. I guess we wanted to solve the correction problem and the BRDF problem at the same time. And the joy of having what you've got here is that you do have pairs. You've got lots of pairs. So we had a lot of imagery, but not that many of them were paired enough that you could actually build a set of equations to solve it. It is inherently solvable. If you've got imagery that's captured closer together, you can solve for a BRDF model and
Yep.
atmospheric connection. I guess we can catch up later as well. It's really interesting.
Yeah, I'd love to talk more about it for sure.
I was going to point out that this is kind of an example of like a processing level that might destroy a potential analysis if
Yep.
you normalize the BRDF, which could have been used for classification.
Yep.
So this idea that there is one analysis-ready data set, to me, kind of strikes me as strange because it depends on what analysis. And this is a very good example.
I 100% agree that we need to think of the right tool for the right job. So, for example, in the Earth Daily mission, if the goal is to have temporally similar data, even if that is the only goal, I'm not saying it is for Earth Daily because people might say otherwise within Urthecast, but if that was the only goal, then you should build the data product for that goal. I don't think there is a single mold for ARD that will work for everyone at all. I think we need to think about who the customer we're trying to serve is and work towards that. And whether that is, as you said yesterday, different processing checkboxes or different processing levels depending on what the customer needs, I love that idea because that helps the user choose the tool they need. But I do think we will need standardized products for users that don't know a lot about remote sensing. And what those are is definitely up for discussion.
Sorry. So I'd like to connect you also on science talk and also self-aware. Very self-aware about what the problems are, what your limitations are. That's terrific. So far, I haven't heard anyone mention topographic normalization as a problem, or as something that's already been solved that is needing to change.
It's not so well kind of rolled into this BRDF problem a little bit. What I would say is going back to, and this doesn't address it perfectly, but this kind of concept of targeting, where is it? Targeting these ideal reflectance surfaces is definitely has to be rolled into that strategy, and part of that is areas of less topographic variation because we know we can't easily correct we can't easily correct for a variety of sun angle effects in the context of steeper topography and things like this. So what I would suggest as a strategy is just down selecting based on kind of topographic flatness. And what that is up for a bit of debate though. But it is rolled into it a little bit.
I think we should end it now for coffee breaks, but maybe any questions could be taken offline.
Yeah.
Because there seems to be some good discussion.
You guys have 10 minutes to go out for questions, but I think there's coffee. We have an opportunity to catch up on the program.
Thank you.
Nice talk.